Hi, class. In this video, I'm going to walk you through my lecture notes on comparing two groups. In this module, we're really going to focus on t-test for comparing means. The t-test is probably the most common statistical test and really focuses on whether two groups come from populations with different means. We're going to discuss one t-test that's used for when you have independent samples or two independent groups and you want to compare the means between two independent groups. And then we're going to talk about another t-test called the dependent samples t-test that occurs when you have the same group measured multiple times. So you can think of that as like a pre-test, post-test situation where you give everyone a pre-test on something, an intervention, and then a post-test. That would be a dependent samples t-test, or sometimes you might hear it called a paired samples t-test. So in the notes, I demonstrate how you would do these by hand. Most of the time we'll conduct these analyses in SPSS, and I've made some separate videos to show you how you would do that in SPSS. But in the notes, I kind of want you to know what's going on behind the scenes. Another thing that's different about my notes than the Kranzler text is this idea of effect sizes. So effect sizes try to get at the practical or clinical importance of your findings rather than just whether the findings were statistically different or not. And we're going to talk about two kinds of effect sizes. One's Cohen's d, and the other one is called omega squared. SPSS does not calculate these for you. And I've complained numerous times to SPSS and IBM, the company that owns SPSS, to add this feature, and they haven't done anything about it. So I've made a separate Excel spreadsheet that'll calculate these for you. But I'll show you how you can calculate them by hand if you're interested in that, and also show you how to use the Excel spreadsheet. In the notes here, I'll also give a lot of terminology that will be coming up. And so I wanted you to have a place where you can reference, oh, he said null hypothesis, what is that? You can come back here and see the definition about it. Or what's a p-value? He keeps talking about p-values. You can see where it's defined here. So I won't read through these to you, but we'll talk about them as we go through the lecture. So in this module, we really get at, one of the main things we do in statistics. We estimate parameters and we test hypotheses. And so each hypothesis test or statistical significance test consists of basically 5 parts. One is what we call assumptions. So each test makes certain assumptions or conditions about the data, and these conditions need to be met in order for the test to be valid. So we'll talk about the different assumptions that all of our tests make. We also have hypotheses. So we'll make a hypothesis or a guess about a population parameter. Typically, what we'll make what's called a null hypothesis, or it's a hypothesis of no difference, because in hypothesis testing, what we're doing, as we talked about in last module, is it's more of proof by contradiction. We're going to start off by saying or making the assumption that the two groups are not different, and if there's evidence, and then we're going to collect data and see if there's evidence in this sample to suggest that there is a difference between the groups. So the test really investigates whether the data contradicts the null hypothesis, therefore suggesting that the alternative, that the groups are different, is actually true. Our test statistic is, the actual statistic that we calculate either by hand or SPSS will calculate that for you. The p-value, or what SPSS calls your significance level, is the evidence against the null hypothesis. So the p-value is really the probability of observing the data that you have, given that the null hypothesis is true. So we're working under the assumption that the null hypothesis is true, and we want to know, well, if the null hypothesis were in fact true, how likely is it to observe these sample data? How likely is it that we would have found a mean difference between these groups of this large? And that's what the p-value tells you. And if that p-value is low, the p-value is small, then that suggests that the null hypothesis is unlikely to occur, thereby suggesting that the alternative hypothesis is true. So the first test we're going to talk about is the independent samples t-test. So the independent samples t-test looks at the difference between two independent group means. So two independent groups, what I mean by independent groups is that scores in one group in no way impact scores in the other. So you may be comparing like boys to girls, or comparing juniors to seniors, where there are distinct people in each group. So the independent samples t-test makes three assumptions. One assumption we would call normality. And so this says that the populations from which the samples were drawn are normally distributed. We're typically not too worried about violating this assumption, especially as our sample sizes get larger and larger. And this is mainly because of the central limit theorem that we talked about before. The central limit theorem says that as our sample size increases, the sampling distribution of the mean approaches a normal distribution, no matter what the actual parent distribution is. So typically we're not too worried about this. And especially when we have a large enough sample. If our sample size is small and and the data are, maybe badly skewed one way or the other, then maybe the independent samples t-test may not be appropriate for that case. The next assumption are independent samples. And so this is basically the scores in one sample no way influence scores in another. That's what I was talking about. If you don't meet this assumption, then you're doing the wrong test, pretty much. This is just the assumption that the groups are independent of one another. And the third assumption is what's called homogeneity of variance. And what this assumption says is that the populations from which the two samples were drawn would have equal variances. If the variances were so different if the variances of the populations were so different, then it could be something else besides the treatment that is actually having an impact. And so this assumption concerns this assumption concerns population variances, not necessarily the sample variances. And so this is an important assumption because it has implications for whether the test is valid or not. So we're going to actually test whether or not we meet this assumption or not. So steps for conducting a null hypothesis. The first step we'll always do is we'll state the hypotheses that we're testing. We'll decide on an alpha level for our test, and the alpha level is simply the amount of type 1 error that we're willing to make. As the researcher, you set your type 1 error. Typical alpha levels are 0.05, 0.01, and 0.001. So that means we're willing to accept either a 5% chance of making a type 1 error, we're willing to accept a 1% chance of making a type 1 error, or we're willing to accept a 0.1% chance of making a type 1 error. And that's just something the researcher decides. Next thing we're going to do is we're going to check the assumption of homogeneity of variance. We'll compute our test statistic. We'll make a decision about the null hypothesis. Are we going to reject the null hypothesis, or are we not going to reject the null hypothesis? We're going to compute a confidence interval, and we're going to compute an effect size. So let's work through an example together. So an educator is interested in the difference in calculus achievement of high school students who are taught under two different conditions. The first condition is a computer-based learning environment where students are taught math concepts via computer models. The second condition is where students are taught in a traditional lecture-based instructional method. So 18 students were randomly assigned to two groups. 9 were assigned to the computer-based class and 9 were assigned to the traditional lecture-based class. At the end of the semester, all the students took a standardized calculus exam. The average, the exam average for the computer-based class was 68.11, and the average with a standard deviation of 11.6. And the lecture-based class had an average score of 49.89 with a standard deviation of 10.24. So was the computer-based instructional method more effective in increasing exam scores? Well, even if the instructional methods were equal, we wouldn't expect the two sample means to be exactly equal, right? So how different do they have to be before we say that, yes, the computer-based instructional method is superior to the lecture-based method? So we're going to use an alpha of 0.05 in this case. So our first step is we're going to state our hypotheses. So in the independent samples t-test, we're testing the null hypothesis that the two population means are equal, right? So that these two instructional methods, there's no difference in these two instructional methods. That's the same thing as saying that the population means are equal. Two instructional methods are equal. So a null hypothesis is always our hypothesis of no difference. If we can then find evidence that suggests that there is a difference, then we will reject that hypothesis. So the null hypothesis is always our hypothesis of no difference. An alternative hypothesis is that the group means aren't equal. We could also propose what's called a one-tailed hypothesis test, where we hypothesize that one method is superior to the other. Two-tailed tests are always appropriate. To use a one-tailed test, you have to have really a justification for why you're only why you're doing a one-tailed test, why you're specifying a direction. And you can read more about the difference between one and two-tailed test here. So the next thing is we're going to set our alpha level. So how much type 1 error are we willing to accept? So in this case, we're told, and I'll typically tell you in your problems, that we're going to use an alpha of 0.05. So we're willing to accept a 5% chance of making a type 1 error in this case. So the next step is check the homogeneity of variance assumption. Actually computing this assumption by hand is actually quite tedious. It involves some other statistics that we haven't covered in this class. So I'm not going to actually compute it by hand. Since we have equal sample sizes in each group, we're typically not worried about violating this assumption. So that's really one way you can get around the assumption of homogeneity of variance, is just to have equal sample sizes in each group. When that occurs, you do have equal sample sizes in each group, then violating this assumption isn't severe. It doesn't have a big impact on the statistical test. In the video where we run the independent samples t-test in SPSS, I show you how you can check this assumption in SPSS. SPSS will automatically give you this test for you. Okay, step 4 is we're going to compute the test statistic. When you do this by the computer is going to give you the test statistic. But if you want to see, this is the actual formula if you were going to compute it by hand. So it's the difference in the sample means divided by the standard error, or this would be the standard deviation of that sampling distribution. And basically what's in this denominator then is sort of a weighted average of the two sample standard deviations or sample variances. So we take each sample standard deviation here, we square it to turn it into variance, and then we're going to weight it by the size of the variance. So that's why it has N1, so the sample size in each group minus 1. In this case, it's basically going to be a straight average because the sample sizes are the same. So here I just worked out the T formula step by step. If you have questions about each one of these steps, let me know. I'll be happy to explain it to you. But then we get a T value of 3.52. Since we're computing this by hand, we either have to look up a critical value for the T distribution or use an online calculator to actually get the probability value. There's a p-value calculator available here. Whoops. Let's see. Where what we do is we type in our T value. What do we find here? 3.52. 3.52. And then we have to give the degrees of freedom for this test. So the degrees of freedom for the independent samples t-test is the sample size minus 2. So there were 9 people in each group. That'd be 18. Subtract 2 from that, would get 16. We get a p-value of 0.0028. So what this is saying is that there was a 0.28% chance of observing this sample, given that the null hypothesis is true. So what's that saying is there was a 2% chance of observing an 18-point difference between these two groups, given that in the population there actually was no difference between the two groups. We're going to say that's a pretty rare occurrence to occur. And so we're going to reject then that null hypothesis that the that the group means are equal, and conclude then that the computer-based method was more effective in increasing students' scores than the lecture-based method. Whenever we reject a null hypothesis, this is when we say the effect is statistically significant, is when we reject the null hypothesis. So let's say, what if the p-value was larger than alpha? Say we got a p-value of 0.091, our alpha level is 0.05. Then what we would do is we'd say we'd either fail to reject the null hypothesis, or we would say we would not reject the null hypothesis. We never say that we accept the null hypothesis because we're working under the assumption that the null hypothesis is true. Remember, the p-value is the probability of observing these data given that the null hypothesis is true. So we're working under the assumption the null hypothesis is true. Let's assume the null hypothesis is true. How likely is it then to observe this difference? That's what that p-value is trying to tell us. So the next thing we do is we calculate a confidence interval. This is similar to what we did in the last module about confidence intervals. It's just the difference between the means plus or minus t critical value times the standard error. So this confidence interval then here is telling us we're 95% confident that the difference between the two instructional methods in the population could be as low as a 7-point difference, or could be as high as a 29-point difference. Remember, we're interested in estimating what the population parameter might be. The confidence interval then gives us our best estimate then of what the population parameter might be. And then in here, I show you how you can actually get then this critical value here. You can go to this website, give it the degrees of freedom, say what confidence level you want, and then it'll tell you the critical value you use for this confidence interval. So the next step, which isn't covered in the Kranzler text, is effect sizes. So our statistical test whether or not the difference in the sample means were likely to occur, given that the null hypothesis is true. But just because the result is statistically significant doesn't necessarily imply that it's practically important or clinically meaningful. And so the effect size helps to provide some evidence to this. So an effect size is a standardized measure of the strength of a relationship. So we're going to calculate what's known as Cohen's d effect size. So it measures how far the samples are from one another in standard deviation units. So we're going to convert the raw difference between the scores into standard deviation units. This is similar to the z-scores that we talked about from before. Here's the formula to calculate Cohen's d. It's just the difference between the means, and here's that weighted standard deviation again, or rather the weighted pooled estimate of standard deviation. We take the two sample means, and we're basically taking an average of them. You can see that the formula is kind of tedious, so that's why I created this Excel spreadsheet for you to use. You can just type in, there were 9 in each group. What were the sample means? 68.11 and 49.89. So that was 68.11, 49.89 were the two sample means, and we need the sample standard deviation is 11.63 and 10.24. 11.63, 10.24. And we get a Cohen's d of 1.66. So, and this is that denominator in that in that formula before, that pooled estimate of standard deviation. That's why it says S pooled here. So there's your Cohen's d. What that's saying is that the difference in the sample means is over 1.5 standard deviation. So students who took the computer-based instructional method scored over 1.5 standard deviations higher on the exam than students in the traditional lecture-based class. Cohen, who developed these or really popularized the use of effect sizes, has some rules of thumb for interpreting them. So he says D's around or greater than 0.8 is what he would consider a large effect. So we would say this is a pretty large effect here. I have a little note of caution here. You really need to know the literature on the subject to really determine what's a large effect. Or maybe large in one field may not be considered large in another field. Here I am using the Cohen's d calculator that I just showed you. And then we'll also do another type of effect size. Omega squared is known as the strength of association. It's actually related to the R squared that we calculated in a regression analysis, or what we call the coefficient of determination. And it's interpreted in the same manner as R squared from regression. It assesses the proportion of variance in the dependent variable that is associated or explained by the independent variable. So here's the formula for calculating omega squared. This formula isn't as, it's basically the t-value squared minus 1 divided by the t-value squared plus the degrees of freedom. You get 0.4. So what's that saying is that around 40% of the variability in calculus exam scores is explained by the type of instructional method. I've also created an omega squared calculator. If you look at the tabs on the Excel file, go down the omega squared tab, you give the t-value, which is 3.52, and then the degrees of freedom for the test, 16. So we get 40.1%. So around 40.1% of the variability in calculus exam scores is explained by the type of instructional method. So it's the proportion of variance in the outcome, our dependent variable, that's explained by our independent variable. And here's a screenshot of the omega squared calculator. Also provided an example write-up. So this is how you would write up the results if you were going to write these up for a traditional journal article. Writing up statistical results is actually quite technical. What you want to do is you want to specify the test that you ran, whether you met the assumptions underlying that test, the results from your test, and interpret your findings. So you can see that's what I've done here. An independent samples t-test was conducted to determine whether calculus exam score differed based on the type of learning environment. Students that participated in the calculus-based exam class, and notice I gave the mean and standard deviation for that class, had statistically higher calculus exam scores than students in the traditional lecture-based class. And notice I gave the mean and standard deviation for that class. And then you give your results for your t-test. We ran a t-test. Well, this should say 16 degrees of freedom here equals 3.52. We gave our p-value, our Cohen's d, and our confidence interval. You can actually interpret the Cohen's d effects as indicated that students in the computer-based class scored over 1.5 times higher on the exam than students in the traditional lecture-based class. That a better way of saying that is they scored 1.5 standard deviations higher than students in traditional lecture-based class. And then omega squared indicated around 40% of the variability in calculus exam scores can be explained by the type of instructional method. Also in here gives some more information about common misconceptions about p-values. The p-value is the probability the null hypothesis is true. That's not exactly correct. Remember, the p-value is the probability of observing the data that you have, given that the null hypothesis is true. Also, some more information on the test of homogeneity of variance. Remember, the homogeneity of variance assumes that the populations from which the samples were drawn have equal variances. So the null hypothesis in this case is that the population variances are the same. That's what we want. So in this case, when we're testing for homogeneity of variance, we actually want to fail to reject this test. We want to have a high p-value in this case because it means we've met the assumption of homogeneity of variance. If we don't meet the assumption, it's okay. We make some adjustments to the degrees of freedom and make some adjustments to the standard error, but SPSS automatically does this for us. To see how to run the independent samples t-test in SPSS, check out that video online. And I'll see you in the next video to talk about the dependent samples t-test. Thank you.